we're going to continue 7-1, and what we're going to talk about is the definition of a parabola. It's still 7.1. Okay, so the definition of a parabola is the set of all points equidistant from a given point and line. That is the definition of a parabola. So, I have this point P and this line L. Then a parabola is the set of all points, so this whole thing here, where each point on the parabola is equidistant from the point and the line. So, for example, if I pick this point, then this distance and this distance are the same. So, like, this is D1, this is D2, D1 and D2 are equal. The shortest distance from a point to a line is a perpendicular distance. So not like the point to the parabola, but from the parabola to the line, that will always be a perpendicular distance. Same thing, if I pick a point over here, okay, then this distance and this distance are the same. Okay, that is the definition of a parabola. So any point along that parabola is equidistant from the point and the line. The point has a special name that's called your focus. And we'll talk more about this when we look at parabolas in 7.4. And the line is the directrix. So I mentioned it yesterday, this first section, 7.1, is kind of just everything's thrown together. So we're talking about parabolas, but then we don't really look into them until section 7.4. We're going to talk about, like, define the other conic sections, but we don't really get into what those are until, like, 7.2 and 7.3. So you just kind of have to hang with it here, and it's a little bit more abstract than the other sections. All right, so what I want to do for this problem is I want to find the set of points equidistant from the given point and line. So my point is 2, 4, so that's my focus. And then my line is y equals -4, so that's my directrix. Okay, so when it asks me to find the set of points, then that's asking me to find the equation of the parabola. So you want to find the parabola that's equidistant from that point in line. So we need to sketch this. So we need to have a sketch to kind of help us figure out what I need to do. I need to remember that every point on the parabola is equidistant from my focus and director. So that's what I'm going to use to help me find this equation. Okay, so here's point P, that's 2, 4. The line is y equals -4. Is that a horizontal or vertical line? Horizontal, so y equals -4, so that means -4 on the y. And that's a line. Okay, so your parabola would be something that looks like this. I'm going to erase that. But here's your parabola, and you want the equation of this parabola. That gives you the set of all the points. So we want to find the equation of that parabola. So I just sketched it in. So I'm going to choose just any arbitrary point, so any point on this parabola. I don't know what it is for sure. I'm just going to pick this one. And all I know is that it's an x-coordinate and a y-coordinate. xy. Okay. What? Should be below what? Well, here's 0.
Oh, sorry, I thought that was.
Here's the line y equals 4. So, yeah, no, it's okay. This is my x-axis, this is my y-axis. I probably do need to label those because there are times where that does look a little confusing, or use a different color. Okay, so what I need to do is I want to show that this distance and this distance are equal. Now, obviously, my sketch is not that great. Those don't look equal, but they should be. Yes?
And then speaking of you, I'm sorry, but like the sketch that you put on the parabola, why did you put it the way you did? Like, why is it like that?
I knew that it has to be between the point and the line. So I really could have drawn it anywhere. Now this I kind of thought a little bit about, because I knew that every point is equidistant from the point and the line, so I was trying to put the vertex kind of halfway between those. But you wouldn't even need to know that. Like, you actually don't even need to have a parabola drawn. You just need to have some arbitrary point between P and L. So it could be, I just sketched it to just kind of help us see like what we were looking for, but I don't know exactly if that's what the parabola is. Okay, so I'm going to call this distance 1 and this distance 2. So what I know is that distance 1 must equal distance 2. So I'm going to use distance formula, which means you need ordered pairs. So you have 2, 4, and you have x, y. I need an ordered pair for right here. Okay? I know that the shortest distance from a point in a line is perpendicular. Okay? Well, this is a horizontal line, so to be perpendicular to a horizontal line, you'd be vertical. Okay, so this point here has the same x-coordinate, right? So that's x. That x is the same. And then what's the y-coordinate right there? -4. Okay? So I was able to write my ordered pair based on this x, y, and I knew that it was on this line here. Okay, So now we're just going to fill out distance formula. So distance 1, I'm going to use x, y, and 2, 4 as my 2 points. Remember, you're writing the equation of a parabola, so it's going to be a quadratic equation. You're going to have x and y when you finish. You're writing an equation. All right, so distance formula, I'm going to do x minus 2 squared plus y minus 4 squared. That's distance 1. And I'm going to set that equal to distance 2. Again, I'm going to start with xy. So I will do x minus x squared plus y minus negative 4 squared. That's distance 2. Minus negative 4, I'm going to go ahead and change to plus 4. Okay, so I'm doing y minus negative 4. I'm going to change it to y plus 4. All right, that's the setting up. That's the part we had to do. That was understanding that we're looking for the equation of the parabola. That was understanding that I had to set those distances equal to each other. Okay, so that's the main idea here. The rest of what I'm going to do is just simplifying this. Okay, so that's the setting up. Now we're just going to simplify. Well, I have a square root equals a square root. Well, so first thing, let's square both sides. Let's square both sides and get rid of our radicals. What is x minus x? 0, right? So, and 0 squared is just 0. So this can cancel. It's just 0. That goes away. Okay. I see that I'm going to have some like terms because I have two y's. I have two terms that have y's in them. So the x's, I'm not going to have like terms because there's just one term with x. Even when I multiply it out, I would have x squared and x, so I wouldn't be able to combine anything. So I'm just going to leave this as is. X. I'm going to move the y minus 4 squared to the right to be with the y plus 4 squared, because I know that I'm going to end up with some like terms here. Okay, so what I'm doing is I'm going to subtract y minus 4 squared from both sides. So that's x minus 2 squared equals y plus 4 squared minus y minus 4 squared. So we see why we did that. We put the y's on one side, so I'm going to have like terms. To combine like terms, you're going to have to multiply these out. So you'll either need to write them twice, write the binomials out, and use FOIL, or you can use that shortcut, the a squared plus 2ab plus b squared. Okay. So if I do a squared, that's y squared, and then I went 2ab. So AB would be y times 4, which is 4y, times 2 is 8y, and then b squared would be 4 squared, which is 16. And minus, I need to do the same thing here for the second one, but I'm subtracting this whole thing, so I'm going to keep it in parentheses until I distribute that negative. So same thing, so y squared, and then 2ab, so 4 times y times negative 4 is negative 4y, times 2 is negative 8y, and then negative 4 squared is positive 16. Okay, distribute the negative, and then we'll combine like terms. So minus y squared plus 8y minus 16. Y squared minus y squared cancels. 8y plus 8y gives me 16y, right? 8y plus 8y. 16 and negative 16 cancels. Okay, well, I'm close. I'm almost there. I'm trying to write an equation. So which is the squared term, the x or the y? Yeah, what I have left, which one has the squared with it, x or y? Yes, x. Okay, so I'm going to get y by itself. I'm going to get y by itself. So you want to get the term that does not have the squared with it, the variable that does not have the squared with it by itself. I mean, think about a parabola and it's a quadratic equation. Right? Think about kind of what that looks like. So divide by 16. So I have y equals x minus 2 squared divided by 16. And I need to clean that up a little bit so it looks like an actual quadratic equation. And so this is my a value I just need to move out front. So instead of divided by 16, that's the same thing as multiplying by 1/16. This is the equation of the parabola, which gives you the set of all points equidistant from P and L. So think about this, going back to parabolas. So the vertex, remember, is opposite of what's inside, and then what's added or subtracted, so 2, 0. I have an a value of 1/16, so it's a really wide parabola, because it's less than 1. It's positive, so it opens up. So if we look at our sketch, the vertex is like right here at 2, 0. Okay? All right. So I had to use the definition of a parabola to help me get this set up, which told me that those two distances had to be equal. I picked any random point. I could have picked a point over here. I could have picked a point right here. Okay, so it just has to be between P and L. Any questions about this? We are going to practice more of these. Okay, not right this minute, but we are going to practice some more, so it should get a little bit easier. Okay, what we're going to look at now is just perpendicular distance from a point to a line. So this example is similar to number 21 in section 7.1. What I have to know is that for my equation of the line, I need all terms to be on the left. I need the right side to equal 0. So not just a constant. I need to move everything to the left and have the right to be 0. You will not have to have this formula memorized. If you need it on homework, then you have it in your notes. But if you need it on a test, it would be given to you. Okay, so first of all, here's my line. I want to know which point is closest, so I'm going to be doing this formula 2 times, because I'll call this point 1 and this point 2. But I'm using the same line, so I need to get this in ax plus by plus c form. So I'm going to move the 2 terms from the right to the left. So I'm going to add 1/2 x and subtract 3. So that'll be positive 1/2 x plus y minus 3 equals 0. So A is what? A is what? 1/2. B is 1. And C is -3. Thank you. Okay, so if I'm going to find the distance from point 1 to this line, I'll call that distance 1. Then this is my x1, y1. So all we're doing is plugging into this formula here. So it's the absolute value of a times x1, so 1/2 times 1, plus b times y1, so 1 times 6.5, plus c, so plus -3, divided by the square root of a squared plus b squared. Okay, so calculate numerator and denominator separately. Don't keep it in radical form if you get a irrational number for the denominator for now. So if we calculate the numerator, then we should get +4. And then the denominator, I just have square root of 5/4 or 1.25. We're trying to see which one's closest, so we can just get an approximation. Divide, you can go ahead and divide, but I would wait to divide until the end. Like, don't round until the end. So if I just rounded 2 decimal places, I get 3.58. Okay. Now I want to see then for point 2, if that's closer than 3.58. So this is now my x1, y1. So I have 1/2 times 1 plus 1 times -1.5 plus -3. And then my denominator hasn't changed because that's still A and B. That still has to do with the line. So square root of 5/4. So I have -4. We should get -4 now. But it's absolute value because distance is positive. So I'm going to get the exact same. Again. So when it asks me which one's closest, I can't really answer that. I just have to say that I have to say that these 2 points are the same distance or are equidistant to that line. So for this section, it's important that you're writing down the directions because you have to understand what it's asking you to do. It's not like you're going to have a section where you just keep doing the same thing over and over. Most of the problems in this section are different. Questions about that? Okay, so we're going to discuss the conic sections that we'll be looking at this chapter. So we kind of start defining some of those. So they're called conic sections because they come from a cone. So whenever we talk about cones, I think about those little water cups that are attached to the big jugs, those little white little cone water cups that I think about to visualize what a cone looks like. So these are sections of a cone. It's basically like if you take that little paper cup and a knife and you cut it into sections, then these are the shapes that would form along the edges. So if you take the cone and you cut it straight across, you will get a circle. Okay. If you take the cone and you slice it across, but diagonally, so not straight across, you get an ellipse. This is in your book, so don't feel like you have to have this all sketched out. Okay, I'll also upload these to Schoology, so if you're wanting to just have that picture, then you can do that. You can try to draw, but it might be a little bit hard. Okay, you can get a parabola if you slice an edge off. Okay? You slice it off, and the direction that you slice it, so like this, you would not have any other section. You get a hyperbola if you slice it, but the direction that you slice it, if you attached another cone, which I'll show you in a minute, to the tip of this, you would slice it up top as well. So what a hyperbola is, it's 2 parabolas is what it looks like. Okay, so I'm going to scroll down. So here is like if you had the 2 cones where their tips were touching, we can see more the difference between a parabola and hyperbola. So think about these like these yellow planes here as like a blade. So if you stick it straight in, it's a circle. If you're cutting it diagonally, it's an ellipse. If you're just slicing an edge off, it's a parabola as long as that angle would not hit the cone underneath it. And then it's a hyperbola if the angle would hit both. So a hyperbola looks like a double parabola. Okay. It's in 7-1. I don't know. Page 632. So this is again parabolas. We've already written this definition down. Okay, we already talked about the focus and directrix. So I don't know necessarily that you need to write this down. The only thing else they have here is the axis of symmetry. Okay, and that line will always go through your vertex and the focus. So this is a horizontal parabola. So your directrix is vertical. The one that we did with that distance 1 and distance 2, it was a vertical parabola and opened up. So then you had a horizontal directrix. So the parabola will not go through the focus or the directrix. The parabola is equidistant from both of those. Okay, so that's your axis of symmetry. Here's your focus, and here's your directrix. This is the point in line. This comes from one of the problems in the book. So this satellite is a parabola. So you can think of this as like the focus, and you would have a directrix down here. Another thing we define in this section is the ellipse. So the ellipse is related to the parabola and a circle. So it's related to a parabola because it has a focus. It actually has two. So we call those foci. Foci. But it's related to a circle because it has a center. Okay, so since there's two fixed points, there's two foci. I'm not just saying distance 1 equals distance 2. So I actually have to have the sum of the distances. There's two foci to be able to draw to. So for example, if I look at this point right here, then what it says is that this distance plus this distance, so distance 1 plus distance 2 is equal to, let's pick a different point, this distance plus this distance. So if I call that distance 3 and distance 4. So that's the definition of an ellipse. The sum of the distances to the foci are the same. Some other parts of the ellipse, you have a major axis and a minor axis. So the major axis is always the longer one. Sometimes that's horizontal, sometimes it's vertical. It's always the longer one. Your foci will always be on the major axis, always be on the longer one, and so will your vertices. So there's 2 vertices. Those will always be on the longer one. The minor axis is the shorter one. And so these points, they're not called vertices. There's no special name. So they're just called endpoints of the minor axis. So we will look into more detail with ellipses in 7.2. Section 7.2. So we just kind of talk about the definition and start talking about some of the parts. That's where we're going to stop today. So we will do more examples of those distance problems tomorrow.